All right, welcome back, guys, to this solution sheet for the paper 5 for the Cambridge International AS and A-level examinations. Hopefully you all had a good exam. Hopefully the paper wasn't too difficult. And paper 5, I feel, is one of those papers where, especially considering how difficult paper 4 is, it's much easier in comparison. And because the questions are fairly straightforward, it's pretty easy to score highly here. So if you guys are feeling not too confident about your paper 4, then paper 5 is where you can easily make up for any marks. So it's a 30-mark paper, and most of the questions, they're very straightforward. There's nothing too complicated, and you'll usually be given marks for just writing the most simple things. So let's just go through the paper, and let's see how this one went. So let's begin. So we're beginning with question 1. The relative molecular mass of an unknown volatile liquid, Y, can be determined experimentally. A student uses the following method to determine the volume of a conical flask. Step 1, weigh a dry conical flask. So you got to make sure that it's dry. So this can be done by, let's say, heating the flask. Maybe don't heat an empty flask that much. Or use a heating, or you can use a paper towel to dry it. Fill the conical flask completely with distilled water. Weigh the conical flask when filled with distilled water. Use a thermometer to measure the temperature of the distilled water in the conical flask. So how do you find the weight of the water? So let's say weight of water equal the weight of flask plus water minus the weight of the flask. So this is weight of flask. This is weight of flask plus water. So you subtract this from that and you're going to get the weight of the water. And use a thermometer to measure the temperature of the distilled water in the conical flask. The student collects the results shown in table 1.1. So again, very straightforward. There's nothing really too difficult about this. So interesting observation. The scale reads up to 0.001 grams. So useful information to go. The mass of the dry flask is 38.126 grams. The mass of the flask filled with water is 168.364 grams. Temperature of the water is 23, and the laboratory atmospheric pressure, so remember that this says kilopascals. So this is 99 kPa, or 99,000 pascals. Always interesting to always be sure, like, just because paper 5 is easier than paper 4 doesn't mean that you're going to get easy marks. So you still have to be careful whenever you're solving this paper and make sure that you're not, for example, missing out on stuff like this that might otherwise cause you to lose marks. So be a bit careful, and I'm sure you guys will be just fine. So let's move on after this. Figure 1.1 shows the variation of the density of the water with temperature. So with most things, we're noticing that as the temperature increases, the density decreases. So again, density basically mass by volume. So when the temperature is increasing, the molecules that were previously spaced out, so this is a liquid, right? So in the liquid, the molecules are sort of far apart. As you're giving them more energy, they start to go a bit farther apart. So this raises the volume, but by a minuscule amount. So volume increases slightly. So it makes sense that if the volume is slightly increasing while the mass stays constant, then the density is going to decrease, right? So that's what the thing is showing. But again, it's a very slight decrease. So notice it goes from 0.99 to over here 0.996. So this is 9958, 99. So this is around 0.9955. All right, so let's go down. Use figure 1.1 to determine the density of water at 23 degrees Celsius. Give your answer to 4 decimal places. So they've already told us how many decimal places we need to give our answer to. So that makes things very easy. So we need to figure out what the temperature is at 23 degrees Celsius. So let's go to the graph. This is 22.2, 0.4, 0.6, 0.8, and this is going to be 23. So I'll just give a line over here, 23 degrees. And in the examination, you'll have better tools. You'll have scales and pencils that you can use. Right now, I'm only using a drawing pad and my hand, so I'm going to try and get this to be as straight as I can. It's not going to be the cleanest line, but as long as we can get a reading. And this goes all the way here. Nice. I think one of the better straight lines that I've done. So let's figure out how much this is. So this is 0.997 and goes up to 998. And between that, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 divisions. So each division is equal to 0.0001. So 1, 2, 3, 4, 5, 6. So that's 6 divisions. So that's 6 into 0.0001, which is equal to 0.0006. You add that to plus 0.997, and you get your final answer of 0.9976. And it's 4 decimal places, so we're going to have to keep it to that. 0.997 and 6. So now we're told to calculate the volume of the flask using the density of the water determined in A1. So again, density is equal to mass by volume. This is density in case you guys don't have physics, so this is the symbol for density. So it's equal to mass by volume. So we're going to have to find out the mass of water. So I've mentioned before, mass of water is equal to mass of water plus flask minus mass of flask. So that's going to be mass of water plus flask, 168.364. So 168.364 minus the weight of the flask, which is 38.126. And that's going to give you a value of 130.238 grams. So you're going to divide this to find the density. 130.238. Oh, wait, we're going to do this to find the volume. So we know the density. The density is just going to be the one over here. So this will be 0.9976 is equal to 130.238 divided by volume. So our volume is equal to 130.238 divided by 0.9976, which gives us a final value of 130.551 centimeter cube. So for the number of decimal places, because you've got two figures over here, one of them is 3 decimal places and the other one is 4 decimal places, you can go either 3 or you can go 4, it doesn't matter. So I decided to go with 3 in this case. All right. So the next question is, another student determines the volume of a different conical flask to be 129.56 centimeter cube. So the volume is 129.56. This conical flask is used to determine the MR of the unknown volatile liquid Y. All right. The following method is used. Cover the opening of the dry conical flask with aluminum foil and secure using a rubber band. So what you're doing is, let's say that this is the conical flask. You're taking aluminum foil and you're wrapping it around, and then you're using a rubber band to sort of hold it in place. So this is to make sure that nothing is escaping, and the rubber band is used to make sure that the aluminum foil is in place. Weigh the conical flask, aluminum foil, and rubber band. Record the mass. So this is just going to be the W weight of the flask. Use a syringe with a needle to make a small hole in the aluminum foil and inject approximately 5 centimeter cube of Y into the conical flask. So now for that conical flask that you've previously had over here, so there's going to be aluminum foil over it. Sorry, that wasn't my best drawing. Like this. And the needle sort of goes in through here. So this is your syringe. a pretty bad syringe, but it's okay. You're not being judged for marks. So that's how the syringe is being inserted into this. Pretend the rubber band is there. I'm not going to draw it to confuse you guys. Place the conical flask in a water bath containing boiling water. So remember, Y over here is a liquid. So you're putting in 5 centimeter cube of liquid. So 5 centimeter cube of the liquid. Place the conical flask in a water bath containing boiling water. Allow all of Y to evaporate. Keep the conical flask containing vaporized Y in the boiling water for a further 3 minutes. This is to ensure that all of Y evaporates. All of Y evaporates. And then carefully remove the conical flask from the boiling water and dry the outside surface thoroughly. Weigh the conical flask, aluminum foil, rubber band, and contents. Record this mask. So you want to dry the outside of the surface to prevent excess water, excess H2O, contributing to the mass. Weigh the conical flask, aluminum foil, rubber band, and contents, and then record this mass. All right. So suggest why the conical flask containing vaporized Y is kept in boiling water for 3 minutes in step 5. So again, we've already mentioned that. So it's to ensure all of liquid Y has evaporated by allowing it to come up to the boiling point of water. Boiling point of water. Here we go, 1 mark. Very simple. Suggest why it is not necessary to determine the mass of liquid Y injected into the conical flask by the syringe in step 3. So again, we're only concerned with the mass of the vapor. So that's why we're not too concerned with, let's say, mass of the liquid Y. So we just want to find out how much vapor has escaped. So that's why we're only concerned with the mass of vapor Y, because when we're doing the calculations, that's what we're going to be concerned with. If you take a look at step 7, weigh the conical flask, aluminum foil, rubber band, and the contents. Record this mass. So you just want to find out how much Y is, been vaporized. So again, we're going to write down, we are only concerned with the mass of vapor Y, as that is used in calculations. In the calculations. All right, student thinks that Y is toxic. Other than wearing safety gloves and a lab coat, state 1 safety precaution that must be taken when carrying out this experiment. So very simple. You're just going to write, because your Y is toxic and it's a volatile liquid. Volatile means that it turns into gas. So whenever you're working with toxic gas, you always want a fume hood, a fume cupboard, whichever one you choose to write. I'm going to write fume hood. So perform the experiment in a fume hood. All right. So far, nothing too complicated. We've been going through this. So let's find out what the next question says. Table 1.2 shows the students' results. So it shows the temperature of the water bath. The water bath is something that you can always control. So it's always at 100 degrees Celsius. Laboratory atmospheric pressure in pascals, 99, so this is 99,000 Pascal. Massive conical flask, aluminum foil, and rubber band in grams is 31.123. Massive conical flask, aluminum foil, rubber band, and Y measured in step 7. So massive Y in flask, the way they got 0.306 is you subtract, let's say this is just, so since we're dealing with mass, let's say this is mass of flask, and this is mass of flask plus Y. So that's 31.429. And the volume of the conical flask used is 129.56. All right. Calculate the percentage error in the mass measured in step 2. So we're dealing with decimal places of 0.001. So we're going to take that 0.00, sorry, that's one extra 0, 0.001, and we're going to divide this by, so basically the formula is percentage error is equal to your error divided by n times 100. So this will be 0.001 divided by 31, because we're measuring, let's say, in step 2. So this is step 2. So because they mentioned step 2, you need to take 31.23. So 31.23, sorry, 123, my bad. 31.123, and you're going to multiply this by 100. So if you do the math, that's going to get you to 0.00321%. So don't forget to add the percentage error, because after all, you are calculating the percentage error. So this will be 0.00321%. All right, moving on. The student assumes that the vapor formed from liquid Y is an ideal gas. The ideal gas equation is shown, where P is the pressure of gas measured in Pascal, so this is going to be 99,000. The volume of the gas in meter cube. So the volume of the gas was, let's take a look at what it says. Volume of the gas, 129.56. So we're not too concerned about that. Number of moles of the gas, we have to figure it out. Molar gas constant is the constant, so this is just going to be 8.31, so nothing to worry about there. Did I not write the volume of the gas? All right, so the volume of the gas, remember, it says it in meter cube. So this is important. We're going to need a bigger arrow. So I'm going to drag this down here. So because it says in meter cube, and this is mentioned in centimeter cube, so this will be 129.56 in centimeter cube. So this will be divided by 100 cube. And if you do the math, then that comes to, let me do a better arrow. 129.56 divided by that gives you 1.2926 into 10 to the power minus 4. So that's our volume. Because remember, 1 meter cube is equal to 100 centimeter cube. So 100 cube, centimeter cube. Basically, if 1 meter is equal to 100 centimeter, so if you cube 1, then you also cube everything else. So 100 cube, and this will be some cube. Simple as. And the temperature, and this is going to be in Kelvin. So our temperature over here is 100 degrees Celsius. So whenever you're converting anything from degrees Celsius to Kelvin, it's going to be whatever the temperature is plus 273. Actually, that should be the opposite. No, that's fine, yeah. So we're going to go 100. So this turns out to be 373 Kelvin. So let's write that down. This is 373 Kelvin. Now, let's plug everything into our formula. So pressure is equal to 99,000 times 1.2956 into 10 to the power minus 4 is equal to n times your molar constant, 8.31 into 373. So n is equal to 99,000 times 1.2956 into 10 to the power minus 4. And then you divide all of that by 8.31 times 373. And you're going to get a nice clean value of 4.138 into 10 to the power minus 4.138 into 10 to the power minus 3 moles. And now we're here to calculate the MR of Y. So N is equal to mass by mR. So now we need to figure out the mass of Y. So the mass of Y is equal to 0.306. So we don't need to worry too much about that. So all we do is we put in the value of the mole that we had, which is 4.138 into 10 to the power minus 3 is equal to 0.306 divided by the MR. So your MR is equal to 0.306 divided by 4.138 into 10 to the power minus 3. And you're going to get a nice value of 73.948. And there we go. 3 decimal place, because the ones that we've been using are all 3 decimal places. So let's take a look at our next question. The actual temperature of the vapor formed from liquid Y is less than 100 degrees Celsius. Describe and explain the effect this has on the calculated value of the MR. So let's take a look at what's going on. They say that the temperature is less than 100 degrees Celsius. So PV is equal to nRT. So let's assume PV and PV is constant. So if PV is constant and R itself is a constant, so the actual equation comes down to PV, and let's substitute N for mass by mR. So this comes out to mass times R times T divided by the mR. So now if your temperature decreases, if P and V were to remain constant, what needs to increase? So if your temperature decreases, the problem is that your since your temperature is lower, your mass can't be the same, right? So because your mass can't be the same, actually, let's not rearrange the equation. Or maybe we can, actually. Just going to explain the effect this has on the calculated value of the MR. Mass is equal to that. So if your temperature is decreasing, well, let's not replace this, actually. So if we're assuming that PV is constant, so let's erase everything over here. The equation comes back to N is equal to PV by RT. Wait, sorry. Yeah, wait, PV is equal to nRT, so PV is equal to that. So as your temperature is decreasing, give me 1 second. All right, so basically, they're saying that the actual temperature of the vapor formed is less than 100 degrees Celsius. So the student actually has no way of knowing that, right? Describe and explain this effect has on the calculated value of the MR. So we calculated an MR over here, right? We calculated to be 73.948. So if the temperature is lower, then what this means is that the number of moles is higher. So if you have a higher number of moles and your mass is sort of the same, then your MR has to decrease. So the actual MR is lower than the calculated MR. This is an interesting question. Honestly, this stumped me for a bit as well because I was confused by the wording. So it says that describe and explain the effect this has on the calculated value of the MR. So the actual MR is higher than the actual MR. And your explanation, as temperature decreases, the number of moles increases, and as mass is constant, the actual MR is lower. Very, very interesting question. That's what I mean when paper 5, while it might be easier than paper 4, it still has a few tricky questions here. The boiling point of methyl benzene is 111 degrees Celsius. Suggest why the MR of methyl benzene cannot be determined using this method. So this is very simple. The boiling point of water, is 100 degrees Celsius, which is lower than the BP. I'm writing BP here. You guys write boiling point in the exam of methyl benzene. So not all the methyl benzene is vaporized. Benzene is vaporized. All right, cool, very simple. And we're done with this first question. There's a few tricky questions, but overall, nothing that we can't get through once we read through properly. So moving on to the second question. Activated carbon is a form of carbon with the ability to adsorb solutes from solutions. The adsorption of ethanedioic acid molecule, COOH2, from dilute ethanedioic acid, COOH2 aqueous, onto the surface of activated carbon is studied in a series of experiments. Before beginning the experiment, 1,000 cm cubes, so this is basically 1 dm cube, of 0.139 mole per dm cube of ethanedioic solution X is made. So this is ethanedioic acid. Solution X is made. The activated carbon is placed in the oven at 120 degrees Celsius for 3 hours. So this is done to remove all H2O. The experimental procedure involves the following steps. Prepare a 100 cm cube of 0.0056 mole per dm cube solution from solution X. Transfer 50 cm cube of that into a conical flask. Add 0.5 grams of activated carbon to the conical flask and start a stopwatch. Shake the flask and immediately remove a 5 centimeter cube sample from the flask. Determine the mass of non-adsorbed COH2 in the sample using chromatography. Repeat step 4 at suitable time intervals until there's no further change in the mass of non-absorbed COH2 in the sample. Solid ethane dioic acid has the formula COOH2 into 2H2O. So let's calculate the MR of this. So this will be C is 12 times 2. So for oxygen, this will be 16 times 4. And for hydrogen, this will be times 2, so 1 times 2. And then we have additional. So we're going to have 1 times 4, and we're going to have 2 more oxygens. This is going to be 16 times 2. So basically the MR is 24 plus 16. 4s are 64, I'm pretty sure. Yeah, 64 plus 2 plus 4 plus 2s are 32. So this MR comes out to 126. So we have the MR calculated. So now let's find out the number of moles. So N is equal to volume in dm cube times concentration. So this is equal to, so we know the volume is 1000 cm cube, which is 1 dm cube. So this would be 1 into the concentration, which is 0.139, which is equal to 0.139 mole per dm cube. So now we know the MR. So mass is equal to, well, actually it's equal to, N is equal to mass by MR. So mass is equal to N times MR, which means 0.139 into MR, which is 126, which gives you a total of 17.5 grams. All right, first question, nothing too hard. And let's take a look at what we're told here. The mass of ethane dioic acid calculated in A1 is placed into a 100 cm cube beaker. Describe the steps taken to prepare 1000 cm cube of 0.139 mole per dm cube ethane dioic acid. Give the name and capacity of any apparatus used. Write your answer using a series of numbered steps. So what you're first going to want to do is 1. Dissolve solid ethane dioic acid in a small amount of distilled water in a beaker and mix until fully dissolved. Until fully dissolved. Number 2, transfer this solution into a 1000 cm cube, because it says 1000 cm cube. What do you call it? Because we're told to describe the steps taken to prepare 1000 cm cube. Into 1000 cm cube volumetric flask. The beaker containing the solution is rinsed. The beaker containing the solution is rinsed with distilled water. Distilled water to ensure all of the solution is added. And then the last step is top the volumetric flask metric flask with distilled water up to the mark, add the stopper, and invert to ensure even mixing. There we go. All right, let's move on to the next question. Is corrosive, so if anything is ever corrosive, you wear stuff to protect your hands, body, and eyes. So you got body covered, eye protection, so you need to protect your hands. So that will be chemical resistant gloves. And we've already answered this before. Suggest why the activated carbon is placed in the oven before use. So this is to remove any water in the carbon. All right, in step 1, solution X is diluted to a concentration of 0.00556 mole per dm cube. Calculate the volume of solution X needed to make 100 cm cube of 0.00556 mole per dm cube COOH2 waste. So, just a very simple molar calculation for this. We need to figure out the volume of solution X needed to make 100 cm cube of 0.00556 mole per dm cube. That. So we're going to work our way backwards. Let's find out what the mole of this solution is. So we need to figure out the moles of this. So N is equal to 100 by 1,000 into 0.00556, which is 0.000556 moles. So now this will be equal to 0.000556 is equal to volume. And remember that solution X has a concentration of 0.139. So this will be into 0.139. You can add by 1,000 because our final calculation is cm cube. So volume is equal to, if you do the math, it comes out to a nice clean 4 centimeter cube. Identify the most appropriate piece of equipment to transfer 50 cm cube of diluted COOH2 in step 2. So this will be very simple, a burette. Suggest a reason why the conical flask is shaken in step 4. Anytime you're shaking something, it's done to ensure uniform mixing. The results of the experiment are shown in table 2.1. So you'll notice something over here. The mass of non-adsorbed COOH2 in 5 centimeter cube sample, 2.5, and the mass of COOH2 adsorbed by activated carbon in 5 centimeter sample. So whatever amount of, so total COOH2 is equal to non-adsorbed plus adsorbed. So using this formula, if we take the time at 0 minutes, then we know that the total is equal to 2.5 milligrams. So keeping this in mind, every figure in this graph should equal to 2.5 milligrams. So, keeping that in mind, this goes from being a rather difficult looking question to just very simple addition and subtraction. But remember to keep the decimal places the same. So 0.60, 0.98, 1.43, this becomes 1.07, 0.99, this becomes 1. This doesn't come 1. It does 1.51 does not seem correct. So this is going to be, let me just pull out my calculator real quick. (1.51 plus 0.99). Yeah, that, okay. So it's basically 1. Yeah, that makes sense. Okay, 0.88, this becomes 1.62, 0.81, 1.69, this becomes 1.70, and this becomes 1.70. So you're noticing that it sort of peaks after a point. So that's interesting, very interesting finding. Plot a graph on the grid in figure 2.1 to show the relationship between the mass of COH2 adsorbed by activated carbon in 5 centimeter cube sample and time. Use a cross to plot each data point. Draw a curved line of best fit. So the way you're going to do this is you're going to take a look at all your values and then you're just going to plot it over here. And this goes on up to 150. So let's plot our graph then, shall we? For this, I think I'm just going to copy this and then draw it on a different one so I can pull the data from here. So times like this one, I wish I had like a scale or something, because drawing a graph freehand is a bit difficult. Always be sure to use a scale whenever you're doing these graph questions. All right. So here, let me pull this out. I use a different color. Why not? We'll do blue for this. Zoom in, make sure we're not too zoomed in. So we have time and we have the mass. So at 0, the mass of non-adsorbed is going to be 2.5. So the mass of adsorbed, so we're going to go, so for our table, we're going to go with these values. So we're going to start at 0 over here. So whenever you're doing graphs, make sure you use a very sharp, very thin pencil. So X over there, at 5 minutes, you're going to have 0.6. Oh, so this is interesting. So 5 minutes. If we assume that this is 10, so 5 minutes would go, let's see if there's anything else over here. So after that, we get to 15. So this is interesting. Okay. So this means that this is 0.2, this is 0.4, and 0.5 is somewhere over here. So this will be that. Next we've got, at 15 minutes, it's 0.98. So 15 minutes sort of comes in the same vein. 0.98. Whoa. And that's at 15 minutes. So this is 10, this is 12, this is 14. So 15 is somewhere here. And now if we go back here, 30 minutes, it's 1.07. So 30 minutes, I think, should be on the graph. Yeah, so 30 minutes is this one, and we've got 1.07. So 1.020406, so 07 is over here. At 45, we have 1.51. So 45, again, these time units are very odd. Usually CIE gives a bit cleaner ones. I'm not sure what went wrong over here, but it's fine. We'll have to make do. So at 45, it's 1.51. So that goes all the way up here. So this is 42, 44, 45. This is 1.5, so somewhere over here. And then for 60, it's 1.62. So 60 gives us 1.62. So if this is 60, yeah, this is 60. And we have 1.62, which finally we've got like a very neat answer over here. 1.62. And 90, it's 1.69. So again, 90 will be, so this is 80, this is 90, and it's going to be 1.69, which is somewhere over here. And then the last for 1.7. So at 120 and 150, it's going to be 1.7. So 120 is this, and 150 is somewhere over here. So that's 1.20. Sorry, this is 120. So, oopsies, there we go. And 150 is over here. All right, and now they say draw a curved line of best fit. So now if we were to plot, it will look something like, again, make sure you draw your one better than I'm doing over here. I'm using a drawing pad and I'm not the best at this, so it's not going to come out the best. But as long as you just have a pencil and you do it in one smooth, yeah, mine's not really smooth because drawing pads are a bit complicated. Try using a different color, maybe that will help. And then sort of straightens that over here. I think that's pretty good. Yeah. And this point over here, we'll take a different color. We'll take yellow. And this is probably going to be anomalous. Let's see what they say. Identify the independent variable. So remember that independent variable is the one that you can sort of change. So like it's the time, right? So instead of doing 150, you could have done up to 200, you could have done 250, and that's going to be the one that you're changing. And dependent is the one that you're going to record. So your independent variable over here is time. So just one variable that needs to be controlled that is not stated in the experimental procedure. Usually whenever you're doing these sorts of reactions, one thing that you should always keep constant is temperature. So I don't recall seeing temperature over here. Let's go through it. Maybe I missed it out. So it says prepare, shake the flask, and yeah, there's no mention of temperature anywhere here. So we're gonna write down over here, one variable that needs to be is temperature. Circle the one point on the graph that you consider to be most anomalous. So we've already done that. Explain the error in timing that may have led to this anomalous point. So is that the one at 30 minutes? Yeah, that's the one at 30 minutes. And so the actual, so let's say, because we're taking a look at when this was taken, this could have been taken before 30 minutes actually passed, because it's much lower, right? If you look at the curved line, the actual one should be somewhere over here. Instead, it's below. So that means that it was taken before 30 minutes of time. So we're going to write down sample may have been taken before 30 minutes. All right, and now we've already done that graph, so we need to worry about that. The experiment is repeated using different concentrations of COH2 aqueous prepared in step 1. The results are shown in table 2.2. M1 is the initial mass. ME is the mass of non-adsorbed. and QE is the mass of adsorbed per gram of activated carbon. A plot of Me by QE against Me is given. Against Me gives the line of best fit shown in figure 2.2. Use figure 2.2 to determine the gradient of the line of best fit. State the coordinates of both points used in your calculation. Coordinates 1 and coordinates 2 include units in your answer. Okay. So first, let's find out the units. So if it's a plot of Me against QE, so ME's units are milligram, and it's being divided by milligram, gram, minus 1. So when you bring it up, it's going to be milligram. When you bring it up, this is interesting. QE is in milligram by gram, minus 1. So does this just come out to gram for that? Me is milligram. Oh wait, they've already given us sort of the Me by QE is given. Let's take a look at the graph first. A plot of Me by QE. So it's Me by QE, and then you further divide it by Me. So Me is already milligram, and QE is milligram, gram minus 1. So Me QE is equal to gram minus 1. Is equal to gram. Because when you take gram up, it turns into gram. So this is equal to gram. And then you're dividing this by milligram. So the unit is going to be gram per milligram minus 1. So that's a quick way of finding out the units. And now for the gradient, you can sort of choose any coordinates. Make sure that you write them down. So you typically want something that's clean. So let's take, for example, something that we can easily see. I'm going to begin with over here. This 9 this 9 is hitting this coordinate really well. So this is 0. Let me see if I can get this straight. Well, not super straight. Let me see. Not good enough. And then this goes down all the way to 9. Oh wait, there's a trick. No, there's no trick. Always use the scale, kids. So this just goes all the way down to 9. So, I'm just going to write down the coordinates over here. So this is going to be 9 and 0.122. So coordinates 1 are 9 and... Sometimes this bothers me so much. 9, 0.122. And the other one that we're going to take is going to be... So for something that intersects neatly. So how about this one over here, which is 0. How about this one over here? So this is 0.2, 0.46. You can take this one actually. 0. So this is 0.6, and this is 0.018. So we're going to go up, and we're going to write 0.6 and 0.18. 0.6, 0.018. So gradient m is equal to y2 minus y1 divided by x2 minus x1. So this is going to be 0.122 minus 0.018. And you're going to divide this by 9 minus 0.6. And you do that, and you're going to get a nice clean value of 0.0124. And we've already calculated the units. The absorption parameter is the maximum mass of COH2 absorbed per gram of activated carbon. Equation of the line of best fit plotted is shown as this. So basically, this is in the form of y is equal to mx plus c. So your x over here is me. Your y is already me by qe. So this is your x, this is your y. That means that the gradient is actually 1 by q0. So 1 by q0 is equal to m. So q0 is equal to 1 by m, which is equal to 1 by 0.0124, which gives us a nice clean 80.65. And we've already done this. And now they're saying the experiment is repeated and the value of QO is calculated to be 78.1 milligram per gram. The total percentage error from the experimental procedure is 6.5%. The data book value of Q is 86 milligram per gram. So they say that if it's within 6.5%, then you can say that it's due to experimental procedure. But if it's greater than 6.5%, then other factors caused the error. So let's figure out what the actual percentage error is. So 86 minus 78.1 divided by 86 into 100, and that's going to come out to 9.2%, which is greater than 6.5%. So as it's more than that, so we're going to say that other factors contributed to the error. And that's that. That's the paper. So paper 5, altogether nothing too difficult. There's some questions that are tricky, but as long as you keep your head cool, as long as you don't panic, and as long as you solve the paper properly, you should be able to get this done and score good marks in this. So best of luck for your examination. If you have any questions regarding anything, again, please feel free to reach out to us. We'd love to help you out no matter what. And yeah, you guys have practiced so hard. You're almost there at the finish line. So once you're done with this, give yourself a pat on the back and celebrate. So yeah, best of luck for the examination, and I'll see you guys next time. Take care.